Hi everyone, in the next videos we are going to prove the strong law of large numbers. In this one I'm going to state it and a few immediate corollaries. So the strong law of large numbers is the following theorem. So it's called strong law of large numbers. Let xi, so x1, x2 and so on, be IID random variables, independent identically distributed random variables, with a finite mean, with mean e of xi, where of course I doesn't matter because they have the same distribution, so it's the same for each xi. And then define Sn to be the sum from 1 through n of the xk. Then the strong law of large numbers is very simple to state. Sn over n converges almost surely, let's put it here, almost surely to this expectation of the xi. Okay, that's the strong law of large numbers. In other words, the probability that Sn over n converges to this mean is 1. The strong law of large numbers is one of the two big theorems we are going to prove in this unit. The second one will be central limit theorem, and to prove each of these will take a lot of effort. So to prove the strong law of large numbers will take a while. Before that, I am just going to state now a few corollaries of it, just to get a bit more familiar with it. The first corollary is the weak law of large numbers. The conditions are the same, so let x1, x2, and so on be IID with a finite mean e of xi. Again, it doesn't matter which I take because they are IID. Again, the same way, Sn is the sum of the xk's for the first n of them. Then the weak law of large numbers says that Sn over n converges in probability to this mean e of xi, which is a deterministic number. Okay? Now, in probability convergence, remember, meant that for every epsilon, the probability that the sequence of random variables which converges to somewhere, so that's Sn over n, which converges to this fixed number, the probability that this is larger than epsilon goes to 0 as n goes to infinity. And this statement should be familiar to everybody. We proved this before using a second moment assumption on the xi's. That we actually don't need. All we need is a first moment assumption. We need to make sure that this expectation here of xi exists and is finite. Under that condition we have the convergence both strongly and weakly. And this is a consequence of the strong law because we already seen that almost sure convergence implies improbability convergence. So that's a really simple consequence of the strong law of large numbers. The second consequence I'd like to show you is two examples. The first example is a simple one. Let Z be uniform on 0, 1, and look at the base 1/2 expansion of Z. So write Z as the infinite sum of L goes from 1 to infinity, AK, let's call it xk times 1/2 to the k, and let's call this k. Xk times 1/2 to the k. So xk's here are either 0 or 1. Homework, everybody convince themselves then these xk's are IID and the probability of xk equals 0, probability of xk equals 0 is 1/2, as well as the probability of xk equals 1. That's also 1/2. Okay, this you can convince yourself. And just as an example, so that we see what's going on, for example, if we take if z happens to be say 7/8, then how can you write this as a base 1/2 base 1/2 expansion? It's 1/2 plus 1/4. That would give you 4 plus 1, 5/8, and give it 1/8. So that's a total of 2 plus 4, that's 6, and 7/8. Okay, so this is the 1/2 expansion of z, and in this case x of 1 is 1, x of 2 is 1, x of 3 is 1, and all the other x's, x4, x5, and so on, are 0. So this corollary is about picking this random number z uniformly random between 0 and 1. So it's not the probability, it's actually 7/8 is of course 0. And in that case, the statement is that these numbers x1, x2, x3, and so on, x5, they are just zeros or 1 with equal chance probability 1/2 each. Okay? As such, the law of large numbers kicks in, and then the strong law of large numbers tells you that the density of digit ones, so these are the digit ones. In this example, the others are digit 0, so these are not ones. The density of digit ones converges to 1/2, because it's probability 1/2, 1/2 is 0 or 1. Okay, so that's a simple consequence of the strong law of large numbers. Okay, let me show you another example. And that's about a very simple version of Monte Carlo integration. So here comes another example. So suppose that there is a function given is a function from the 0-1 interval to the 0-1 interval, and I want to find out the integral of this function. And for some reason I can't get this in a closed form, so I want to have a numerical algorithm to find this integral. One way to do it is take x1, x2, x3, and so on, and also y1, y2, y3, and so on, IID all together, so x is independent of y and the sequence itself is independent, so everybody is independent of everybody, uniform on 0, 1. So take a doubly infinite sequence of uniform 0, 1s, define rho I to be the indicator that g of xi is bigger than yi. Okay, so this could be either 0 or 1. 1 with probability. 1 with probability, well, of course, probability that g of xi is larger than yi. Let's calculate this probability. So what is this probability? G of xi bigger than yi. Well, it's a double integral on exactly this set. G of x larger than y. Double integral of the joint density of these two uniforms, namely xi and yi. It's the same for each I because these are IID. The uniform joint density is just 1. And then we need to perform a double integration here. Okay? Now, it doesn't matter in which order we do this integration. So actually, if we do the integral in x first, then, sorry, in y first. I want to do this in y first. So gx bigger than y, the boundary is the same, dy and dx. So I want to calculate this inner integral. What is this inner integral? It's the integral of y from, obviously the uniform of course lives in 0, 1, so all the integral is of course between 0 and 1. So let's add this here, 0 and 1. So in particular, y will go from 0 to 1, except that y has to stop at gx given x. So if I have my integral in x on all of the range of x, which is 0, 1, then given x, y has to go between 0 and g of x. So if I go between 0 and g of x in y, then I simply get the integral from 0 to 1 of gx dx. So this probability here, same thing, actually is equal to my integral I'm after. It follows, because rho is an indicator, that E of rho I, because it's an indicator, its expectation is equal to the probability of the event it indicates. So probability g of xi larger than yi, which is the integral from 0 to 1 of gx dx. And of course the rho i's are IID, because the xi yi pairs were IID. It follows that if I look at the sum from 1 through n of the rho I, I divide by n, this will converge almost surely to the expectation of the rho I, which is the integral from 0 to 1 of gx dx. Now if I want to find out the numerical value of this integral from 0 to 1 gx dx, then one thing I can do is generate these uniform random variables xi, yi's, calculate whether this event occurred, gxi is larger than yi or not, count how many of those occur up to time n, divide by n, and almost surely as n goes to infinity, this will converge to my integral. So this is a simple example of something called Monte Carlo integration. Where a deterministic question is answered by using probabilistic method and random choices and just simulating the randomness and calculating the relevant random quantity, which will then almost surely converge to the quantity we need.